Welcome everyone, and today's speaker is Atri Day. She's one of our new postdocs here at DIAS, and she's going to tell us about Muon G-2 and type X two-Higgs-doublet scenario. Thanks, Atri, and I hand it over to you.
Yeah, okay. Yeah, good afternoon, everyone. So today I'm going to talking about one of my project, which is in Muon G-2 and type X two-Higgs-doublet scenario, and some high scale, some studies in high scale validity. And this project is based on, this talk is based on our paper, which is published in PRD with my collaborator Joyita Lahiri and Bishwar Mukhopadhyay. And so I'll go through these things one by one. So first I will give a brief motivation of our work, then the model, which is here is a two-Higgs-doublet model, and a few things about Muon G-2, which is Muon anomalous magnetic moment. And then I will go through the constraints from current LHC data and the other experiments in our model. And then I will go to our results. So here's the motivation. So right now, we all know that normally there's a long-standing discrepancy between the standard model predicted value of Muon anomalous magnetic moment and the experimental observed value, which is recently means the data coming from our Fermi lab data, and we have already a data from our early BNL data. And so recently there's a long-standing discrepancy between these two, and which is near about 4.2 sigma right now. So whatever particle we have in our standard model, it's not sufficient to describe the Muon anomalous magnetic moment, which is experimentally observed. So which can hint towards some new physics. And for this one, type X two-Higgs-doublet model is a good candidate which can explain the observed Muon anomaly if we can allow a extra low mass pseudoscalar particle, which is in our two-Higgs-doublet scenario. But the problem is, if the pseudoscalar mass is very small, then our standard model Higgs can decay to pseudoscalar pair, and the LHC experiments have a strong bound on Higgs decay branchings, and the current limit on Higgs to A, which is our pseudoscalar particle, cannot be more than 4%. It is coming from our LHC data. So the question we asked in this project is that can type X two-Higgs-doublet model, which can explain our Muon anomalous magnetic moment, and also it can give us any hints of the UV completion for this type X two-Higgs-doublet scenario. So the first is the model. So here we just looking for a two-Higgs-doublet model. This is the general two-Higgs-doublet potential, where in standard model we only have one scalar doublet, but here we have two scalar doublet, phi1 and phi2. So this is the most most general scalar potential we can write. But here the thing is, we introduce extra Z2 symmetry, and so our phi1 and phi2 have different Z2 charges here. So, but we just allow a softly broken Z2 term in terms of this M12 square, phi1 dagger phi2. So, and all the parameters, all the quadratic couplings here real. We are looking for only this scenario. And the thing is, after spontaneous symmetry breaking, so after spontaneous symmetry breaking, both of our Higgs-doublet can have wave, which is V1 and V2 for phi1 and phi2. And so after spontaneous symmetry breaking, we have two CP even physical state, which is small h and capital H. and alpha is the mixing angle between among these two states. And so, and also we can have a CP odd neutral-scalar particle, which is A, and also a charge Higgs, which is H plus minus. And the mixing angle in this sector, in the CP odd sector and the charges sector, is beta, and which can be parameterized as tan beta, which is V2 by V1, the ratio of the waves. So we have so right now we have the modified gauge couplings with respect to our standard model 1. So this GSMV is our standard model gauge coupling, which is which can be calculated or can be means like the experimental bound is already there from LHC data on GSM. In our model, so there's an extra scale factor which is sine beta minus alpha for our neutral, means our standard model Higgs with coupled with when it's coupled with our vector bosons. So there is an extra this multiplicative factor sine beta minus alpha or cos beta minus alpha, depending on in which CP event states we are looking for. And the current LHC limit on Higgs branchings put a strong limit on sine beta minus alpha. So we can't vary sine beta minus alpha, like it should be very close to 1, +1 or -1, but it should be very close to 1 from our current constraints. And
was that sine or cosine had to be close to 1?
So sine is close to be 1. Yeah, sine is close to be 1. Means the mod value of sine is close to be 1. And which we just referred as alignment limit. So we called this is our alignment limit, where sine beta minus alpha tends to means +-1.
Can I ask about
Yeah.
You have two Higgses
Yeah.
and they're both complex for 4 degrees of freedom now.
Yeah.
But there are 5 fields here. Oh, is that calculation plus or minus the same as the calculation?
Yeah.
Oh, I see.
Yeah,
So it's the same.
same,
Okay,
same.
sorry.
Mind V1 and V2 were,
The wave of phi1 and phi2.
and the V2 was obtaining phi1 and phi2.
Sorry.
Properly broken. The V2 that was properly broken.
Yeah.
That exchanges phi1 and phi2.
Means exchanges means like yeah. Phi2, yeah.
Can we say the branching into once?
Why was that? Was it two symmetry? Why was it pi1 was 9, pi1, pi2, pi2?
So that is related to the way they come to fermions, and the fact that this not actually working with 5 is, but I think you can.
Yeah.
But then why is it properly broken?
Because due to this extra M12 squared term, means like there's a no hard Z2 breaking terms, which can change our which can give us a kind of extra divergence in our.
If I take phi1 to minus phi1 and phi2 to minus phi2.
Yeah, it's one of they have the
Just one of them.
yeah, they have different Z2s.
And can I see where the CP violation is in?
Sorry.
Can I see where the CP violation is going wrong?
No, so here all the terms are real, so there's no CP violation.
Yes, so it's coming from, it's in the fermion sector.
Yeah.
By the
Yes,
individual
yeah,
coupling.
yeah. Okay, so sorry. So yeah, so after that, so we have our physical Higgs, means like physical scalar masses and our mixing angles. So we can write down our quartic couplings in terms of our physical Higgs masses and mixing angles. And this is the after all the calculation, after the diagonalization and all the things. This is the relations between means among the mixing angles, masses, and our quartic couplings. So yeah, and so that yeah.
What was the V in that? Right?
So yeah, so this V is square root of V1 square plus V2 square.
Okay.
The total wave, which yeah. Yeah. So and here we are looking for a type X two-Higgs-doublet model. So the thing is, in type X two-Higgs-doublet model, there's this V2 symmetry which prevents phi1 and phi2 both can't like couple with leptons or quarks. And this is because of we are just avoiding 3-level flavor changing neutral currents. So like the lepton masses can only come from like phi1 wave, and for quarks it's just for phi2. So here for type X two-Higgs-doublet scenario, there are other two-Higgs-doublet scenarios also, but for type X our phi1 can couple with leptons, not with the quarks, and the phi2 can couple with the quarks, not with the leptons.
So
Yeah.
type X has phi1 as the standard familiar Higgs. Is that what you mean?
No, so that would be type one.
Yeah.
Where phi one couples to quarks and leptons.
Yeah. Yeah.
I thought you said type X.
Yeah.
Yeah. Type X.
It says phi one leptons and phi two coupled to quarks. So phi one would be the one that you're thinking of, in which.
That's called type 1.
That's what-
Yeah, that's called type
Oh, I
X.
see.
Yeah.
Type X.
Okay, so right now the factors by which the standard model Higgs interactions is scaled in this model. So this is in terms of the sine beta minus alpha, cosine beta minus alpha, and this kappa factors. So we can see that here our like pseudoscalar coupling with fermions, like pseudoscalar coupling with leptons actually is proportional to tan beta, and our pseudoscalar coupling with quarks is proportional to 1/tan beta. So if we are in a region where tan beta is large, which is allowed from the experimental data, then we can use this factor for our and I will discuss it. How can we use this large tan beta minus alpha to adjust with our Muon G minus 2 anomaly, and how can we use it? So here another thing we can one can notice that our sine beta minus alpha and cos beta minus alpha, they can be plus or minus, they can be positive or negative, and depending on the sign, our this YHF term can be positive or negative. If we are in a large tan beta minus alpha, we are in a large tan beta region, then if our cos beta minus alpha is negative and sine beta minus alpha is positive, then we can have a negative Yukawa coupling in this region. And so for our case, so we have looking for two different scenarios. One is right sign scenario, which is basically the standard model scenario, where the right sign is called like our standard model Higgs coupling with the fermions, and the standard model Higgs coupling with the gauge bosons have same sign, and for wrong sign, they have opposite sign.
Let's go back to the previous slide actually. Is little h got an electric charge?
Sorry?
Does little h have an electric charge?
No, it's the standard model Higgs. Small h.
The capital H of the charge. Does capital H have a charge? In the previous response, say use capital H plus or minus.
No, so this
Indicating the capital H was charged.
No,
Okay.
but one is
Yeah.
the charged one, and little h and little h are
the two CP even states.
So I'm confused. Can you go back to the response where you showed the H's?
Yeah. What is capital A for H plus and
You
minus?
get capital H, little h, capital plus and minus. and
It's
capital
a
H.
charge scalar, capital H plus minus. Is
So
it
the
another
phi-
particle?
so the phi scalar here.
So you have two different.
Yeah.
Yeah.
From the two charge fields that mix,
Yeah.
you get a master
Charge boson boson, yeah.
And then you left with one charge case.
But the field in this slide, the calculation of the H. Capital H plus and minus is different from capital H.
Yeah.
So the
Yeah.
phi field-
What do you
Yeah.
count it plus minus is two particles or
Oh, of course.
one?
Yeah.
No, it's from one unit.
Yeah. Then it's fine. Yeah.
And
It's
there's,
fine if you do that.
yes,
Yeah.
there's the each calculation and there's
And this is A.
But there's only one field.
well, no,
No.
two complex.
Well, there's 8 there.
Yeah, there's 8 there. Yeah.
Okay, so the other 3 degrees. Oh, there's the masses.
Yeah, so there's a Goldstone bosons.
Yeah, I see. And which combination of the 5?
Which complex?
Where does the WZ get the masses from? Which combination of 5 and 5?
Which common?
So she hasn't shown that explicitly there, but you see, she says that it's the angle beta that diagonalizes the charge mass matrix and the odd mass matrix. So it would be well, the same equation that she
Yeah.
derivation did,
Yeah.
but we can replace alpha with beta.
Like this is,
B1, B2.
yeah.
And just to clarify also, the quarks and leptons are getting their masses from different Higgs.
different doublets. Yeah, means yeah, because each doublet means like the physical masses are like when we are in a physical state, then they are mixed up with phi1 and phi2 with some mixing angles. Okay, so yeah, and our scenario here is we are just consider our small h is our standard model like Higgs. Yeah.
You have these scaling factors. How am I supposed to interpret these scaling factors?
Scaling factors means
You use you said the factors by which the standard.
yeah, so means like it's the normal standard model Higgs coupling with like fermions like leptons. We have this mass like m f by v kind of things, and along with this there is an extra factor.
You just
This.
this is to be multiplied by the.
Yeah, with the
Okay.
standard model.
So as she did the alignment in which sine beta minus alpha is 1.
Close to 1.
So that would say, yeah, the cosine beta minus alpha is 0. So the y middle HFI would be
Very close to 1. Yeah. Yeah.
Where the y capital HFI would be.
Yeah, so
Close.
justification for what this is that it must be just very weakly off the standard one
Yeah.
because the second Higgs is playing very little role in.
Okay, so yeah, so in our scenario, our small h is our standard model like Higgs, have masses 120 nearly 125 GeV, and the other Higgs is means other CP even neutral particle is capital H, and it always have a mass which is greater than 125 GeV. So we are looking for in this scenario where the capital H is the heavier one.
Just with regard to the values there, how close does it have to be to
This capital H and
this angle? How close does it have to be to how large can I make cosine?
oh, so like for sine beta minus alpha, the limit is like we have to choose a
The
value.
cosine one is probably easier because it's small. How small
Yeah,
does it have to
so
be?
It's very small actually. Like I know the value of sine beta minus alpha, which is close to 0.999. And it also depends on the other parameters. Means not for the whole range of sine beta minus alpha, you have to be greater than 0.999. It also depending on the tan beta and other parameters.
That's 1 minus 10 to the
Yeah,
minus
minus
3.
2.
Yeah, so that tells you, of course.
Yeah.
So-
Okay. So yeah. So now the muon G minus 2. And so the anomalous magnetic moment of muon from normal quantum mechanics. So this gyromagnetic factor G should be, but if we are also just consider the radiative corrections, then it should be not 2. There's some extra correction factors, and so this actual this anomalous magnetic moment of muon is parameterized in terms of this a mu, which is g mu minus 2 by 2. So the classical result for g mu is 2, but there's a quantum correction, so that's why there's some deviation from 2, and this term is parameterized as a mu. And so the most recent estimate in standard model is this value. So our a mu should be this, where this term, the number inside the bracket is 1 sigma theoretical uncertainty. And also the most recent experimental bound, which is coming from the Fermilab data. And also if we come, yeah, so 1 sigma plus minus 1 means this is 1 sigma value, so like the mean value plus minus 43. And yeah, so if we combine our Fermilab and BNL data, then our recent experimental data which tells us our a mu should be this. And so there is a like 4.2 sigma discrepancy from the standard model calculation and our experimental data. And for the standard model, these are the diagram, Feynman diagram, which can contribute to radiative corrections. Here we are only.
Hasn't that 4.2 sigma gone down with recent?
So yeah, so
lattice results which were updated.
Yeah, so they are just recently they just claiming that the lattice QCD data they have they have extra contributions in from this light by light calculations of this things. But yeah, but for the last Fermilab data when they published their paper, they just took this data. So yeah.
So the last thing was like new simulations. It was on the prediction side.
There was a BMN simulation, and then there was a more recent one which involved the Planck. Then I think they bring the
maybe they 3 point not 3, maybe 3.4 or 3.5 sigma. Yeah, but at least there is 3 sigma discrepancy still there. So these are the normal standard model diagrams which can contribute to our radiative corrections along with the normal one. So there can be QED corrections which has a like large contribution in radiative correction of muon anomalous magnetic moment. But recently they have started like all QED contribution up to 5 loop they calculated. And there are other electric processes where also Z can replaced by Higgs, standard model Higgs. And they have calculated this process up to 3 loop. So they have this much precision. And there are the hadronic QCD contribution, which they have calculated from this lattice QCD method and some data-driven method. But yeah, so it's not. And so along with this thing, so as in type X two-Higgs-doublet model, we have extra CP events Higgs and extra CP odd Higgs. Also, we have extra charge scalar. Then there are extra diagrams which can contribute to our muon G minus 2. And so there is the major diagrams in type X two-Higgs-doublet scenario, which can give an explanation of muon G minus 2 and with a good agreement with our experimental data. So we have one loop diagrams also in type X two-Higgs-doublet scenario. But the thing is, along with this one loop diagrams, the major contribution is coming from this 2-loop Bargee type of diagrams because they have a extra loop suppression, but the thing is they have an enhancement factor of this m square by mu square, where this m is the fermion or this like charge Higgs boson mass or the fermion mass, which is running in this triangle loop. And if this fermion is like our top quark or tau or something, then there's a huge enhancement factor. And also another thing is here that we are looking for a low mass pseudoscalar. And also the pseudoscalar coupling with our leptons is proportional to tan beta. And our recent experimental bound can allow to take the tan beta value like at least till 100. So then the major contribution will coming from the first diagram. And so among these three diagrams, most like 96 or 97% contribution is coming from the first diagram. So
How large is m squared over mu squared? How large is that enhanced?
like it's yeah, so
And then use 100 milli. So it's 1700.
Yeah, so it's quite, yes, it's
Yeah.
quite large.
Yeah.
10 to 6.
But that technically means that you have that the perturbative analysis is not so reliable because you will find these such triangles embedded elsewhere in your calculation. There'll be higher corrections,
yeah,
which will also be enhanced.
But is this,
yeah.
these
But the-
are saying they're enhanced over other diagrams? In the perturbative
Over
analysis?
the-
Yeah, over the other diagrams, like
No, but actually the two part diagrams and the logic.
Yeah.
And one.
Then the one
because
that-
on the one part, we have two electrons with muon couplings, means, which would be one. Because square is very small, but if you look diagram with the upward in middle, then you would have one muon or the coupling times the couple power, which is one. So the reason the second order is contribution rather than the first order is not because perturbativity problem. And the third, three loop diagram, something happening with well, they don't have a significant.
You have a significant three loop dots.
no.
Well, you still have the.
Yeah, we will also have a 1/16 pi square loop separation extra.
The 1/16.
16 pi square, kind of like for every one loop, like
Those new coefficients grow rapidly. Once you get into loops.
Yeah, but it has been changed. The calculation of the time.
Yeah.
Okay.
okay.
Because you have a total power instead of electron or muon power. You see, the one.
In one loop, yeah. So I have the one loop diagram, but in my backup slide maybe.
But I think it's problematic if the two loop is larger than the one with them there, but the other means three loops. You really would need to check. It's something it's oscillating,
Well, it seems like that.
which I think you can't rely on the perturbation.
I think it's actually calculated, not perturbatively as well, but it is just because of that one diagram with the top, in. That is, that's for the last contribution. If you go to the third three process, even if you put the top power in there. If you go forward, yeah, but.
You have more chance.
The particles and the loop separation factor, it has been checked that the third three processes don't have.
The fourth loop is what we worry about, because if I've got an oscillating, then it's not. Less experience.
Remind me when the fourth loop is higher than the third loop, the contribution is smaller than the second.
Well, you know that it's divergent series. The real point is you know you're the divergent series. Normally in a divergent series you stop and your reliability goes down when the coefficients start increasing. So you stop when they start increasing. Otherwise you have to do a isolation.
Yeah, so what she said in the beginning was that they have been calculated up to 5 years.
No. this electric.
And they're monotonic.
Yeah, so only, yeah. Okay, so yeah, so here the first diagram actually contributes a lot among these three major contributions also. So which can give us 3 sigma upper and lower bound coming from the experimental observed central value of delta mu in MA and tan beta plane. MA is the mass of our pseudoscalar and the tan beta. So as we can allow our tan beta like of the order of 100 also, then and also our MA can be very small. So this diagrams has a major contribution, and this whole YOLO region actually is right now the region which can explain our muon anomalous magnetic moment up to 3 sigma. So for our rest of our calculations, we will only look for this region also, this YOLO region in MA tan beta plane.
And what are these red ones?
Yeah, so the red one is the early BNL data. So we have the early BNL data when this restriction is not, means the region is not so much restricted, then the patch was like the red one, but after this Fermilab data, the region is more restricted, and we are only can allow only this YOLO region up to 3 sigma.
The yellow region is the shaded one.
Correct, yeah, YOLO.
Why is there some red green arrow?
Sorry?
Why is there some red dots leaking the green arrow?
Oh, so no, so that's like a normal a scan. So it's like, so that's why it's not there's a lots of points and we just plotted it. So that's why there's in few regions there's a red points. But the thing is this 2 lines, this 2 YOLO regions, there's a lower bound and upper bound on coming from this experimental observation. So we can only look for this YOLO patch, the whole YOLO patch. So that's not the issue.
So with the upper bound and lower bound on the observation, like there were 2 values. The experimental one.
Yeah, so yeah, central value, and there's a plus 3 sigma and minus 3 sigma.
Right, okay.
Yeah, so there's this value. So now, along with this, our type X 2-Higgs-doublet scenario have other constraints from other experimental data, like data and the precision measurement data and something. So we also have to consider these constraints for our calculation. The first constraint, which is coming from the electric precision measurement data. And so we know that if in our model we have extra scalars and extra charge scalar, then they can contribute to our W boson mass or G boson masses via loop. But we know that like we can we have the precision measurement for this W boson mass and Z boson mass. We know the value of them and the error bar also. So we can't allow extra scalars, which is like with any mass or any couplings, because they can affect our W boson mass and Z boson mass. So these constraints are coming from this precision measurement data, which tells us that we should restrict our delta M, which is the mass difference between our CP even states and the charge X state. And for when, as we are looking for a low MA region and large tan beta, then we can allow maximum 50 GeV for this delta M. So our parameter space should allow this kind of constraint, means should follow this kind of constraint. So we can't allow delta M greater than 50. And there are other theoretical constraints which includes perturbativity, vacuum stability at electric scale. And from the vacuum stability constraint at electric scale can put a bound on our quartic couplings in type X two-Higgs-doublet scenario. So this. So yeah, these are the constraints. This is the constant, but we can see that from the last equation. So these lambdas can be written in terms of our physical Higgs masses and mixing angles. So if we just look for our last equation, then we can write down this lambda 3 plus lambda 4 minus lambda 5 in terms of our physical Higgs masses and the mixing angles. And the thing is, there is a term like YHL sine beta minus alpha, which can decide that we are in right sign region or we are in wrong sign region. So for this, our sine beta minus alpha is close to 1, and our YHL also has to be close to 1 because it's like sine beta minus alpha minus cos beta minus alpha into tan beta. And from the LHC data, which also should be close to 1. So this factor, the whole factor should be close to 1, but it can be positive 1, which is right sign region, and can be negative 1, close to negative 1, which is our wrong sign limit. So depending on the sign of these two, at large tan beta limit, if we are in right sign case, which demands that our YHL times sine beta minus alpha is close to +1, then this can put a bound on our heavy CP event states, and we can't go beyond 250 GeV from our vacuum stability and perturbativity constraint for low M. But for wrong sign Yukawa scenario, there's no this kind of bounds, but there are perturbativity constraint on other lambdas, where all the quartic couplings cannot go beyond 4 pi. So from there is a constraint on M capital H, which is 870 G.
Remind me, which couplings are getting the wrong sign?
So yeah, so the wrong sign is, yeah. So our Higgs coupling with fermions and Higgs coupling with this vector bosons, which is scaled by the sine beta minus alpha.
The Higgs coupling with the for this in the standard one conditions. I can't absorb that sign. What is telling me the sign of the
So what is line B?
This YHV is our sine beta minus alpha. This standard model coupling with sine beta minus alpha.
Yeah, what is this X coupling for the X field which elements?
This gauge boson.
Oh. No, just the count of it.
So when you have the 2 X's that couple to W and Z, then the coupling is shared between the two of them. So in this equation which you did, y little HV squared plus y capital HV squared y standard model.
So the standard model is only complicated.
Yeah. Yeah.
So with the 2 Higgs and some.
It's according to the y.
Yeah.
So the same combination.
Yeah, it's just coupling of Higgs with WW or with CZ. This kind of couplings. Yeah, gauge couplings.
So that's what she called, but in the standard model, she called it GSMP. Whereas in the two-double model, she called it Y of HB. So you see, if you were in the Higgs alignment there, or if you didn't have the second Higgs,
So can I think of it as a direction of the vector?
but it's exactly the Higgs talking to WW
Yeah.
and ZZ.
Hmm.
But in the standard model, you only have the Higgs that does that. In here, you also have this other scalar. So you have little h.
But the standard model is two couplings, the higher coupling is two couplings. Next one, two different case couplings.
Yeah.
And
Like,
well, I need to see the actual.
Yeah.
I need to see that.
Yeah.
Yeah.
It's
Means any coupling like it's, yeah.
that coupling is paired between the two.
Yeah.
Yeah.
Cities and there.
These are feeding into the powered. And all of the power couplings, if we can't find opposite sign.
No, so
No,
she
no,
said,
no, no.
maybe show this part where you have where you define the wrong sum, yeah.
Yeah, so we have this YHV, and we have this scale factor YHF, and so the right sign is when both of these Y factors have same sign.
Okay, that's.
It's +1 or -1,
So
Very
the
simple.
key is that these factors have opposite signs.
opposite sign.
Why is it called the right sign? It's not flat and same.
Yeah, in standard model, both of these are positive normally, so that's why it's called right sign.
So when it's going to change if the decay is, but it can't affect, it must, if I
Oh.
change the sign of the power
No,
it's the.
in LHC data,
decay
no,
that it's going
no.
to-
No, because it's all the, like, whatever in LHC they can observe, it's the cross-section branchings, this signal strength. And the signal strength is like, whenever this coupling is coming, it's just square.
That's what I'm expecting.
Yeah,
So
that's why we can.
how can you be sensitive to the sign of that?
No, so from LHC data, that's why we can have both sign. So we have a freedom to choose right sign and wrong sign. But in our model, if we are choosing wrong sign or right sign, then there are some constraint coming from the theoretical point of view that we can't have a Higgs, other Higgs, the mass cannot, means it should be less than 250 GeV. We can't find other Higgs, which is like of the order of 500 GeV or something in this model. So if we can, like,
I'm expecting that in the standard case, I should be able to change that sign by changing the vector multiplication value of the leads. The sign of the multiplication. Is that?
So like
It's a
in
convention that it's possible, I suspect.
Yeah.
Like, yeah.
The standard model is, the sign of the sign of a single coupling and picture.
yeah.
It's a convention.
It's like changing the sign of one.
Exactly. So all of them changing plus to be plus here, that's a convention that all of them have the same sign, that's true.
Hmm.
They don't have the same sign.
Yeah.
The reason why it's not the same sign.
I'm not sure who you.
Can I ask, what is YB in the standard?
So in standard model,
is it
it's
a
just-
coupling, is it actually two coupling or is it some combination?
So like here, what we are talking about, like any standard model coupling with like Higgs with WW,
What's
yeah.
GB in the standard? Is it the U1 hypercharge gauge coupling, is it the SU2 gauge coupling, or is it some combination?
So that's the
It's
vertex
just,
factor
yeah,
of
vertex factor of Higgs
ZZ.
to ZZ or Higgs to
Yeah,
VV.
the Higgs coupling, both SU.
Yeah, both, yeah.
Yeah.
So
Yeah.
some combination of U1.
Well, it's after the.
Yeah. Yeah.
So, what is the talking of the Higgs Z? So for Z, I think it's, okay. We actually calculate.
So it's the Higgs ZZ.
Yeah, Higgs ZZ effective
Yeah.
coupling, yeah.
For the Higgs WW coupling is the G2.
G2, yeah. This
G2B. With
So then-
G2V, there's one,
Combination
yeah.
of the SU gauge coupling.
Yes.
Yeah, for
Yeah.
ZZ, yes.
Some combination.
Yeah.
So WW is G2.
Yeah,
Yes.
G2V, yeah, some,
Then the-
yeah, yeah.
So for G is combination. for
Yeah.
W is.
So whatever it is,
G
like,
is taken to that one.
So GV, two actually things. So
Yeah.
Use the notation of B representing.
yeah,
those
yeah,
forces.
yeah.
If you write it for Z, it's a combination of G1 and G2. If you write it for W,
First, just for my
G.
Okay, yeah.
I'm just kind of speak confused as to there's a right sign versus wrong sign. I'm not sure that there is a wrong sign in the other model.
So in the standard model, she said the reason she put it right sign is because what is happening in the standard model. Which is the power couplings. Well, actually, only power
I think it's an
couplings.
extension.
Yeah.
It's not a model you take a convention.
Yeah.
Yeah, convention.
So she says for the standard model,
Okay.
With that, with this standard model convention, it's a.
Yeah.
so she says in this model, you have the option of, one of the couplings being negative, or having the opposite sign, the power coupling.
So you choose one of them to start on convention, and the other one might get. Yeah.
So that would, you were arguing at no observable significance.
Well, I expect the amplitude should involve square margins.
Yeah.
So it's very unlikely that it would, that sign would be observable.
Yeah, so actually, at the LNC, they can, well, they have, defined the sign of all the power couplings to be the positive one. For the top, it was quite difficult, but, they have recently come up with a method of, doing it so they can, clarify at least positive. Yeah. Exactly, yeah. Yeah.
So it is a physical thing that you can see that the signs are
Yeah.
all the same.
Yeah.
Okay.
It's a question of whether when you're on the couple comes into the Higgs coupled with the Fermi and want to take it in there. So you define the positive, you say the massive positive.
So it's a relative thing.
The relative
Massive,
positive, and you say it's Y five.
Yeah.
Right.
Okay, so this is the thing, and so there are other constraint which I already discussed, that if our pseudoscalar mass is small, then our standard model Higgs can decay scalar pair. There's an on-shell decay, and so, but from the data, they have put a strong bound on this decay branching, which cannot be more than 4%. But here the another thing is, so if we demand that our standard model Higgs decay branching to A is very small, then the standard model Higgs coupling with A should be small, and it should be tends to 0. And actually experimentally it already explained that this GHA has to be of the order of 10 to the minus 3. So here, if we can write down this YHL times sine beta minus alpha in terms of lambdas and the physical parameters, this mixing angles and all the things. And so here we can see that. So if we demand that we are at electric scale, our theory is perturbative, and also we demand that our HA coupling is very small, then we only can have a wrong sign region in our model when MA is less than MH by 2, when there is a chance of on-shell decay of Higgs to A in this region only. So in this region, we should, from the theoretical constraint and the experimental constraint, we should be in a wrong sign region for our model. Yeah.
Have you observed H2A? What is the signal?
Yeah, so H2A is like lambda 3 plus lambda 4 minus lambda 5 V square kind of.
Yeah, what do you see at the LX when you look for H2A?
So this bound,
Yeah.
Higgs to A, yeah. So this Higgs to A bound is coming from like our pseudoscalar can decay to tau tau and mu mu. So they have such like 4 tau channel and 2 tau 2 mu channel. And from there they put a constant like it has to be less than 4%.
But how strong is the bound if A is heavier than half of the mass of the Higgs?
It's very small actually. Then actually if A can be like greater than 62.5, then there's a no on-shell decay possible, but off-shell decay can be possible. But then the limit is 4%. That's not an issue. Like this limit is coming only from the final state calculation. But then the Higgs, like there's not available phase space for this decay, and the decay branching actually drops down very fast. Yeah. So and also we also tell that our sign beta minus alpha should be close to 1 from like Higgs to WW or Higgs to ZZ decay channel searches. And so considering all the things, all the available data, all the available constraint in our model parameter space and all the theoretical constraint also, now we allowed our parameter space, we put a scan in this range where we choose our MH, M capital H and MH plus minus from 125 GeV to 870 GeV. And MA, we keep it small, so it's 20 to 100, tan beta is same. And sin beta minus alpha, right now we just write from 0.99 to 1 because like it's depend on the value of tan beta, means the limit is not like 0.999 for all tan beta. It depends on the tan beta. If tan beta is very large, the limit is very strong on sin beta minus alpha. And also this M12 square, we just choose this value because for the perturbativity constraints, if we have to like be a perturbative region for our λ1, then our M12 square cannot vary like from this value like mh square by tan beta very much, then it will break perturbativity. So we are just keep in this region, we are in this region. So after that, here is our parameter space after running. So the left side plot represent the parameter space for wrong sign region, and the right side plot it's for right sign region. So the red points and blue points, they are the points which is allowed from the theoretical constraint. And now we can see that if our MA is less than 62.5, there is a chance of on-shell decay of H to A. Then also you have to consider the branching of this HAA constraint coming from LHC. Then we can left with this only yellow dots. So these are just a fine-tuned region. And also this green line is our 3 sigma upper and lower limit coming from Muon G minus 2 data. So in our model in wrong sign region, if we are looking for a region of parameter space which can explain Muon anomalous magnetic moment and also the all constraint coming from LHC data and other constraint and theoretical constraint, then we can choose a region of parameter space like this yellow dots between these two green line and the blue points above the green line. So this our allowed region at electric scale for our model in wrong sign case. And the right sign case, we already seen that like we can't have a region of parameter space when MA is less than 62.5 because then means like because it's right sign, and I already explained that here we can't have a right sign case when HGG is very small. So in right sign region, we can have a parameter space only these blue points above this green line in typex.
So wait, that's what you said in the right side case, only the blue points that are between the green lines are allowed.
Yeah.
And they give the correct T minus 2 contribution.
Yeah.
And the left one, the yellow dots and the blue dots.
Yeah, yellow dots between these two green line and the blue dots.
So it doesn't look like there's many yellow dots, but is that because of the simulation?
Yeah. There's very fine-tuned region actually.
So you expect that the yellow dots are going to fill out that whole?
No, actually, no, we can't. We means like you can see that the density of points at very low tan beta is large, and when you go up, then it's like very small. At like all the points we have, it's below tan beta is 60. And also it's very, very fine tuned.
Why are there a discrete number of points? This is like a continuous parameters space.
Actually, it's also it's a marginalized plot in tan beta MA plane, but like other parameters, other Higgs masses and all the things can run in this region. And there is a problem to satisfy the other theoretical constraints also.
So if I looked at like in between two of the little yellow dots,
Yeah.
close,
So
actually in between them, there might be a point where it's not out.
I think you're asking why there are dots there. I think she's just doing the numerical complications
Yeah,
of difficult
yeah.
integrals.
Yeah, so
Yeah.
then I was thinking, well, so if that's the case, then, you know, what's the diagram that you expect if you can work this out analytically? Is it just entirely yellow? But then I thought the answer to my question there was, no, it's not entirely yellow. And then I'm wondering, well, does that mean that actually in between some of those dots, there are invalid parameter sets?
yeah, maybe if we run like for more data points and we can access the more data points, then the plots we can have another few points also.
And like in the
but
infinite.
Yeah. Actually, yeah, means like here we can see that the probability to have a point greater than 60 is right now it's kind of very small. So like the thing is we can't compute that much.
Yeah.
So whatever we have, like we can see that the density of points at low tan beta region is very large, and when it's just at large tan beta region, it's very small. So this indicates that in this region, it's a very fine-tuned region. Means it's not like to have a yellow dot which is greater than 60 tan beta, then our other parameters should be very fine-tuned.
Yeah.
Means very much fine-tuned. And so yeah. So
You
that's
say that in principle it's possible to fine tune enough so that you can hit any point in that space.
yeah, maybe, but it's very fine-tuned region. So
Okay.
usually people are not interested in that much fine-tuned region because it's very impossible, because there's a lots of parameters and we can't find this much fine-tuned region.
Yeah.
So that's
All right. So like on physical terms, you want to be somewhere in the space of parameters where it's like kind of more likely that you get those.
yeah. So there's a like this looks like there's a small probability to have the points in large tan beta region, the large probability to have points at small tan beta region.
And how precisely are the points evaluated? How much
Precisely.
confidence do you have on that given point when you evaluate? You're doing a numerical calculation for
Yeah.
variation. Is it a Monte Carlo calculation, some integrals, or what way do you do that?
No, means like for this one, like we have a random number generated in this region.
Select a random number.
Yeah, from 125 to 870.
And what you're putting them into. I'm not sure what is behind this calculation. What it is.
So like we know that we need a Higgs to A branching fraction less than 4%.
You're calculating those loop diagrams.
Yeah, so not means yeah, like we know the structure of the coupling constraint and the factor. So in terms of this coupling and the other factors, there are other factors with this HGG coupling, and with this HGG coupling is depending on the lambdas.
But the final factor depends on the. You don't know that accurately. Do you know the final factor to high precision?
Means like high precision means like for a tree level Higgs to A decay, we know that what is the branching. Like we can calculate the Feynman integral, and there is like after over the full integration, we can have the branching fraction in terms of the couplings. So like.
So whether it's calculating analytic machine knows.
Yeah. What is
But the experimental bounds that come out of LHC come with the precision.
Yeah.
And I understand that. But I
Jump around. Why the thread between the dots? Yes.
What's the rate between?
I mean, these are analytic functions,
Yeah.
and I would expect continuity.
Yeah, but so you see, there's a, like each grid point has many other parameters.
Yeah. Involved in the.
Yes.
Which change and they come from, well, experimental bound on them.
Hmm.
So you start by like uniformly sampling from the things at the top, the intervals at the top.
Yeah.
You pick those parameters and then you put it into some function. that-
Yeah, for each point, yeah.
with
Yeah.
Their plus and minus,
Mhm.
minus blah, blah, blah.
Yeah.
And then that spits out one of these points.
Yeah.
And so you're kind of sampling like a regular lattice from the however many dimension interval at the top.
Yeah.
Set of parameters, right?
Yes, so what the plot is showing is the G minus 2 contribution, which is something, the function that she's got analytically.
Hmm.
And then the points that she's given in those intervals, they're also cut down based on whatever the experimental things that she's got. And then, yeah, at the end, those two green lines for the region, the experimentals observed for G minus 2.
So you get, and like you have an error bar on all of these dots coming from the error bar of the standard from.
I mean, no.
So like error bars, like it's a normal theoretical calculation, so.
So in that calculation, you use standard model parameters that were measured.
Yeah,
So they all have.
they also have some
Yeah.
error bar, yeah, yeah.
So then,
but-
so
But this error, so the thing is, like. If we just use this value delta mu, no? So this in delta mu, all the theoretical error bars coming from the standard model is already there.
oh, right, okay.
Because it's delta mu, so we have experimental error bar, theoretical error bar, and the errors are like square root of both square plus square.
So when you calculate one of these dots, you don't use.
No, and we know the delta mu error bar, 1 sigma error bar. And we allow the 3 sigma, like, so we have a 260 central value times 10 to the minus 11. Just forget about it. So 260 plus minus this 3 sigma value. So whatever points we have there, so this point should like give a contribution like 260 in between 260 plus minus 3 sigma.
And the points sitting on top of each other, which don't necessarily have the same.
Same, yeah, yeah.
Right? The two points sitting on top of each other might have the same area and tan theta.
Yeah.
But you have.
With the other MH and other sine beta minus alpha, they are different. Because all the parameters are marginalized. Yeah.
All right, so like, that makes more sense. You couple the density of the stuff.
Mhm.
Yeah. Okay, okay.
Oh, I mean, that kind of is a dangerous question also, like, I mean, if it's a prediction from high dimensional space, then the continuity may be in a different direction. Than this is the. I mean, the continuity here is I cannot see, because these are actual responses. And but the continuity might be in different kind of, different.
Like a top is eating again, for the shape.
Yeah.
Okay. So
Sorry, I didn't. So, you probably said this, what was the reason you weren't going to lower time?
no, because we just trying to have this muon G minus 2.
So,
Like,
if MA was lighter.
MA cannot be so lighter because like then there's a constraint on MA also like.
Then why didn't you lower time?
Yeah, so we can't because we have a heavy Higgs and this like heavy Higgs can go to tau tau and from LHC heavy Higgs searches they have a bound on tan beta. They can't. So yeah, so there's a similar plot for wrong side and right side in image tan beta plane, and here the like so this kind of distribution we can see that so like for large tan beta, our allowed parameter space prefer to have a image which is close to our standard model Higgs. Like the plots are like that. If we demand a very large tan beta, then our two CP event states has to be nearly degenerate, like their mass cannot vary.
And which region in this plot gives you a two-minus-two?
So the whole region,
Oh,
yeah. So this is the whole region. So is the allowed.
so what is, oh, wait, you can say what it is.
Mhm. And so after that, actually, whatever we calculated yet means still, so it's only calculated at electric scale. So our model parameter space at electric scale, these parameters are this model parameter space are allowed. And the electric scale we set at like it is at top quark pole mass, which is 173 GeV. So right now, like we use the two-loop RG equations, the RG running of our lambdas, and like we're just trying to investigate that how they can evolve at higher scale and get this domain of validity in the light of our vacuum stability and perturbative unitarity, and which can give us a cutoff scale lambda UV cutoff for different means like for each points, like for each point in our parameter space of type X two-Higgs-doublet scenario, which is allowed from all the constraint at electric scale, then this means this region means like up to which scale it can be like sustain the perturbativity or vacuum stability itself. So for the to see the nature of the RG evolution, we choose two benchmark points in our scenario. First, so our BP1 is a point where our heavy Higgs is much heavier, like of the order of 450 GeV, and for BP2, our heavy Higgs is like 150 of the order of 150 GeV, and it's close to our standard model Higgs also. And we can see that. So, and depending on these things, the lambdas is calculated at electric scale. Then we just trying to evaluate the lambdas with energy. And we can see that for BP1, as our heavy Higgs mass is large, then mostly the lambda 3 and this lambda 3 actually start from a larger value at electric scale. And that's why this point can sustain the perturbativity only up to 2 TeV. Like after 2 TeV, the perturbativity of this theory for this particular benchmark point will break down. So for BP1, our lambda UV cutoff is at around 2 TeV. But for BP2, as the two Higgses are very close to each other, our lambda 3 starts from a smaller value, and itself it can be a perturbative theory till 10 to the power 13 G.
Is there a sort of physical summary of why when Higgs are really close to that?
Yeah, because when actually it's depending on these equations, I can show you like yeah. So you can see that it's like very much dependent on this mh square minus m capital H square minus m small h square. And also we can't allow our sine beta minus alpha very different from 1. And our tan beta is also like large. So
So the
it's
perturbativity breaks down with that difference square.
yeah, because
The breakdown perturbation is not necessarily breakdown in physics. No. Just mean you're using all you have to do different reasons. Is the potential stable? That's a physical question.
yeah, this potential like for the benchmarks, yeah, at electric scale this potential is stable.
But you run off for the standard model.
Yeah.
It depends on top quark mass, but the potential becomes unstable.
Yeah, so we also like not the perturbativity, we also consider vacuum stability, perturbativity, unitarity, all the constraints in your yeah. It's good. Means the lambda UV cutoff scale means that like whenever it's breaks the perturbativity or vacuum stability or unitarity, anything, we just stop at that point, and we called it lambda UV cutoff. And so now we just proceed to scan the model parameter space to look for the points which is satisfied all the theoretical constraints like vacuum stability, perturbativity, and unitarity up to various cutoff scale from 10 to the power 4 to Planck scale. And there are two scenarios. We already discussed that we have a scenario with wrong sign Yukawa and right sign Yukawa. And here's the case 1, which is wrong sign Yukawa scenario. And the same plot in MA tan beta plane. So right now, the blue points, the points at electric scale, which can be valid up to 10 to the power 4 GeV, like from the vacuum stability, perturbativity, and unitarity issue. And the green points are points which is valid up to 10 to the power 8 GeV. Red are valid up to 10 to the power 16 GeV. And the yellow points are valid up to 10 to the power 19 GeV, like Planck scale. And there is this Muon G-2 bounds also, like 3 sigma bound. And when we just put all the bounds like Muon G-2 constraints and all the collider constraint and all the things, then we can left with the right side plot. So here we can see that if we just trying to have a regional parameter space which is fine-tuned, but then also which can be valid till Planck scale in this theory, then we have to be in the region where MA is greater than MH by 2 and tan beta is very large. So and this is very clear in this plot also, like so this is the same plot in MH tan beta plane after putting all the constraints. And we can see that, so we can have some YOLO points, which is valid up to 10 to the power 19 GeV at electric scale. So these points are plotted at electric scale, which have a high scale validity till 10 to the power 19 or 10 to the power 16 GeV, something. So we can see that. So if we demand a regional parameter space in type X two-Higgs-doublet scenario, which can explain the Muon anomalous magnetic moment as well as all the experimental and theoretical constraint, then and also it's valid up to Planck scale, then we should have a MH which is very close to 125 GeV. So our 2 CP event states has to be nearly degenerate and our tan beta has to be very large. And also our charge Higgs mass and our CP event Higgs mass also, they also has to be nearly degenerate. So all our CP event states, not the pseudoscalar, has to be nearly degenerate. Our pseudoscalar has to be small, means like low mass, and tan beta has to be very large, like at least 60 or something, to get this kind of scenarios.
Why do you care about running to the Planck scale?
Sorry?
Why is it important to run this to the Planck scale?
It's like it's not important, like we just demand, like if we can have a regional parameter space which can itself valid till Planck scale, like we don't need any extra theory before Planck scale. So like our standard model is so yeah, so right now the case 2. So case 2 is the right sign region, and the similar kind of plots we can have here also. So we can see that here also in right sign case, we can have a regional parameter space which is valid till Planck scale also. And when MA is greater than MH by 2 and tan beta is very large, and also our 2 CP event states and our charging states, all of them are nearly degenerate, then we can have a regional parameter space which is valid till Planck scale. So yeah, so then the conclusion. Here In this work, we have explored the high scale validity of type X two-Higgs-doublet scenario, and particularly in the region of parameter space, which can have a low mass pseudoscalar particle, and which can also explain our muon anomalous magnetic moment, and which is perfectly agreed with our experimental data. And also after that, in this parameter space, we just applied all two loop running of various couplings in such regions up to various high scale, means like from 10⁴ to 10⁻19 GeV. And thereafter, we identifying a region of parameter space, which is perturbative, which is valid, like from different valid till different cutoff scale, and which can sustain our perturbativity, vacuum stability, and all the things, and also can explain the current experimental and theoretical constraints. So yeah, so that's all.
Any question?
Yeah.
Thank you. So that was like how it can be a candidate for this, for explaining the D-2 discrepancy. But then, so how much do you know about showing that it's the right candidate? Like, what predictions were the signals of this theory over and above what we've seen so far?
So like not only the muon G-2, the other signatures of this model.
Oh, right. So okay. So, well, yeah. So I guess you could look at that as a signal of this model, but then you might be saying like, oh, but just come up with a model to fit this discrepancy, but it doesn't do. Surely it does all these other things you detect. Or
You get lots more than particles.
Yeah. Okay.
For one.
So that's something that you then we need to also be able to see in the LH.
So you mean, how would you know if you have a type X two-Higgs-doublet?
Yeah. So like so there are from other Higgs searches and something, there's scope to have extra particles in ours. It's not the standard model, also it can be the other particles also. And the type the two-Higgs-doublet model is a simpler way. Like we have one doublet in our standard model. The next step we can imagine that why not we just add extra doublet, and which can give us some extra particles, and we have some parameter space which can allow from our LHC data or something. So that's why they just started on these signals. And there are also like lots of searches in this Higgs-doublet scenarios also, like which perfectly agrees our LHC data in different channels, in not only Higgs searches, in also the other channels, like because they're also like if we have extra particles, they can give us new signatures also in other channels.
Yeah.
So in that sense, actually, right now there are lots of hope, and like especially the type X scenario, we have a like a good amount of parameter space is allowed from our all the current data. And so yeah, and
space you can work out where there's money. In the future, if we push the energy up a little bit, you'd be able to see it in some process.
Yeah. So like there are some this kind of works also where people just say that if we have this kind of parameter space, then in future LHC we should get this kind of signals. Like in this channel, in a particular channel, we can have like 5 sigma discovery or 5 sigma discrepancy from our standard model background. So they have this kind of works projections. And if we can't find anything in that energy scale, then this parameter space should be not valid. This kind of parameters in this model. So
the signal that you use as an experimental bound on the model is because nothing's been seen in those channels.
yeah.
But if the precision of the experiment was higher and we actually see something in those channels, you could use it as not just proof that this is one of the models that could be in the
Right.
So what is the explanation for seeing only one Higgs-doublet and not more? Unless they're very highly acid?
No, means you can use the extra Higgs doublets also. These models also have their signatures, but the simplest way one can think, like first way, that just add one Higgs doublet. And if we can have like, if we just have extra one Higgs doublet, then we can explain all the constraint and all the data. So means you can add extra doublets, like
Surely
3
they can
doublets
add-
also.
Can you see if you found only one Higgs-doublet? Is that right?
Not one Higgs doublet, yeah, or only one neutral Higgs.
If they find another new things, then
Yeah.
you don't know if it's a problem. It's stuff that where you think that
Singlet, yeah, triplet,
if they
yeah,
find charge states, then
yeah,
you know that it's not coming from a
singlet,
singlet.
can't have it, just, yeah.
If they find another charge.
Yeah. Then there should be triplet.
That's right.
Yeah.
Yeah.
I'm going to go to turn off the recording. And I discovered that the microphone upstairs is on, where the X-ray is now.
Okay, the primary to match the number of propagating directly.
Yeah.
And here the story would be that, well, this is the 2D story, but by the time they come to the propagating freedom, differently you can find out the thing.
And we right now, so we found one scale, but we still can't rule out that it might be two mass degenerate scales. The signature would look exactly like what we've seen. But if the other scalar was there, then yeah.
So why don't 3, 4, 5?
How does it differently?
Can we report?
If it's a mass degenerate,
Yeah.
we haven't ruled out that possibility.
No.
Is that what for other markers as well? Like, when you make a similar, or is it just Higgs in your understanding?
Well, the Higgs is the latest particle we discovered, but we won't say that we discovered, and we already told about it. It's a lot easier to discover charge particles. So, for example, the clouds that there are on another fermion are much more stringent.
Yeah,
than
yeah.
they're found on other scales. We haven't really, experimentally, the scalar factor is not really that accessible yet, but we look at it as one of these. If we've got other colliders that use factory, then
Yeah.
we can definitely look in that direction.
Because like if you had a double or the general mass, okay, there are some physical consequences of having that kind of model. Do you actually see something, or is it?
I don't think so, yeah.
So in that sense, would it not be like it might be the same name as like age type thing, where it's not something observable. So talking about that scenario is like,
I'm not sure. Do you know, Brian, if it's something that is theoretically impossible to distinguish if you have two degenerate cases?
Would that not change your thing? Because what is the case we've done?
Well, what if they're sharing the cross section?
But you made a cross section compared to one section. If the two of them was not basically equal in the case as well. But you can't tell them apart.
If you can't tell them apart.
The case was
Right?
the case was cross section the case could be more equal.
What if, well, the coupling for half of what we think they are?
or
So,
so you have two fields that are independent degrees of freedom, and both got their they're mathematically the same, and then they're just
Yes.
Yeah, for all the physical properties that are there, when.
Yeah, so,
That sounds like I want to.
yeah,
Yeah, it sounds like you probably do some sort of field, we don't have anything about it, yeah.
yeah.
It depends on being an office.
Maybe if this was a suitable one, higher multiplex,
Yeah.
and there was lots of them, they were all accidental. Yeah, nothing between themselves.
But the doublet and
Sorry to interrupt for 1 second. Is it okay if I stop the recording?
Yes.
Yeah.
Just to, I want to just come back down. So, okay, thanks, Atri, for an excellent seminar, and thanks again.
yeah, people.
I'm going to stop the recording.